AOPS Volume 1, the basics, number 91. To find the smallest positive integer, which when divided by 10 remains 9, divided by 9 remains 8, divided by 7 remains 6, etc., all the way down when divided by 2 gives a remainder of 1. And this question can be approached many ways. And this question is also infamously known to many students. And if you have not attempted this yet, I recommend you to attempt this before you listen to my understanding and to my explanation of how to solve this. And I'm going to be solving this through modular arithmetic. Now, modular arithmetic is especially useful and very convenient when applied to questions which revolve around remainders and divisions between numbers. So let's get started. We need to find this number. So we suppose the quantity that we're trying to solve for. So let's let this number be equal to x. And if this number is equal to x, then some following of modular statements must exist. I'm not going to be going over modular basics and the modular definition in this video, for it will cover too much of this lesson period. So I'm just going to get straight to it. If you don't understand modular arithmetic, then please do consider checking out videos previous on where I explain what a modular is before checking out this video. So a modular 9, so let's say x mod 9. So actually let's do mod 10 first. X must be congruent to 9 when mod 10. X must be congruent to 8 when mod 9. X must be congruent to 7 mod 8, and so on until x is congruent to 1 mod 2. And all of this is saying is just that x will have a remainder of 9 when divided by 10, x will have a remainder of 8 when divided by 9, and etc. So with this, we can apply a modular property. That is that if we have a statement that a is congruent to b mod n, then a plus 1 must be congruent to b plus 1 mod n as well. So therefore, we can apply this to this question to get x plus 1 is congruent to 10 mod 10, x plus 1 is congruent, x plus 1 is congruent to 9 mod 9, x plus 1 is congruent to 8 mod 8, and this goes down all in all until x plus 2, or x plus 1 rather, is congruent to 2 mod 2. And what does this mean that each is congruent to the modular 10, 9, 8, etc. to 10, etc. to 2 rather, sorry? It means that x plus 1 must be divisible by all 10 numbers between 1 and 10. Why is that? Because if x plus 1 has a remainder of 0, only then can it be congruent to 10 mod 10. So this is the same thing as congruent to 0, congruent to 0, congruent to 0, congruent to 0. Therefore, we must conclude and deduce from these statements that x plus 1 must be divisible by numbers between 1 to 10. So to find this, we must also find the smallest positive integer for which is divisible by 1 to 10. In other words, we need to find the greatest common multiple of 1 to 10. And I do this because that's what the question is asking for. So now that we have these statements down, we can begin to find the greatest common multiple. And to do that, the easiest way is through prime factorization. So this is 10, 9, 8, 7, 6, 5, 4, 3, and 2. I wrote this all down because I want you to have a good visual understanding and conceptual understanding of what is about to go down. So what is 10 equal to? 10 is equal to 2 times 5, 9 is equal to 3 squared, 8 is equal to 2 cubed, 7 is equal to 1 times 7, 6 is equal to 2 times 3, 5 is equal to 1 times 5, 4 is equal to 2 squared, 3 is equal to 1 times 3, 2 is equal to 2 times 1. So we must find the greatest common multiple. Therefore, we need to factor out and take out some multiples within each number that can be found because I just listed it all on the left of the screen. So greatest common multiple of 10. 10 has to be multiplied by 2 and 5. So we must take out 2 and 5 here. And you see here that since we're taking out a 2 and 5, it covers both 5 and 2 because we have the multiples of 2 and 5 within our greatest common multiple. Now we move on to 9. 9 is equal to 3 squared. So this must multiply by 3 and 3. Subsequently, by doing this, we have found a multiple of 3 within this greatest common multiple. And then moving on to 8. 8 requires 3 2's to get, but we only have 1 2. So we need to multiply it by 2 more 2's. Hence, we got this out the way. And subsequently, we got 4 out the way because 4 requires 2 2's and we already have 3 2's. So that is sufficient. What is 7? 7 can only be found by 1 times 7, so we must multiply this by 7. 6 is equal to 2 times 3, which is already covered with 2 and 3 present within this multiple. Hence, multiply these up and we will get our greatest common multiple between, or least common multiple, sorry, is supposed to be least common multiple of numbers 1 to 10. So 2 times 5 is 10, so we're going to leave this on the side and multiply this out to get a quick and concise answer. 3 times 3 is 9, 2 times 2 is 4, that's 7. 4 times 7 is 28, times 9 should give us 252, hence multiply by 10 will give us 2,520, which must be equal to x plus 1. Because remember, x plus 1 must be divisible by all 10 numbers. And the least common multiple of these 10 numbers is 2,520, meaning that x plus 1 must be divisible by 2,520, meaning x must be equal to 2,519, which is the solution to our question. And you see how elegant and simple this solution is. And the reason why, if you still do not understand this, is because of this statement right here. This statement is what helped me derive this answer. X plus 1 is congruent to 10 mod 10, meaning that it must be divisible by 10. X plus 1 is congruent to 9 mod 9, meaning it must be congruent to 9, and it must be divisible by 9. So this just is a basic modular understanding that it has to be divisible by all 10 numbers. Hence, I can say to do what I just did with the prime factorization, finding the least common multiple, and finding x to be 2,519. Nonetheless, that's the solution to this infamous question.